Thank you for the introduction. And actually, you described very well what I want to do. And what I did is really go over the old papers and so on. And I will try to present a perspective how really technological developments motivate people building software on those new technologies, and then motivate the computer science people to develop principles and a scientific understanding of those systems to improve them and make them better. So as Peter said, trying to focus a little bit on blockchain. So I mean, what are blockchains? So I'm sure you more or less know what they are, but there are so many different ways of looking at blockchains. Let me present a very simple perspective for what are blockchains. Is just this kind of huge creature that is a universal computing machine. And what is special about the universal computing machine is that it's running on top of many computers. It's always accessible, anywhere, and unkillable. And what do I mean by a universal computing machine? It's really just like a state machine, a distributed state machine, because it's running on top of many computers. And what it does is simply at any moment there is a state in which the machine it is at the current moment, and it's receiving a sequence of commands from anywhere, from everybody. This is one of the novel things that you don't even know to. You do not need even to identify the participants a priori, and these participants anywhere they can at any moment issue commands, each one commands, and somehow these commands are ordered and executed sequentially, so that the state of machine changes accordingly as a response to each of the commands. And what is wonderful is actually that this state machine has two really impressive properties, being built on top of so many computers and with unknown users somehow, that the history of executed commands can be examined by anybody at any moment and is tamper-proof. Once this sequence of commands are executed on the state machine, nobody can pretend some other different commands were executed, nobody can change them, and everybody can look at this sequence at any moment and verify what is happening and in which state is the state machine. So the question is, of course, how do you build such a creature? How do you control it? How do you understand it? How do you know exactly what's going? What are its properties and so on? So this is the goal of the talk, is really to try to trace back the history of the ideas and technologies that led us to this exciting future where you can actually build these creatures and you can understand them and so on. And what is very nice is I had a lot of fun looking at the old papers, tracing back older and older papers, and what I discovered is that in some sense the modern history can be traced to a story that starts in the early 60s, and which I will describe a little bit in this talk, and through a series of milestones that I will discuss. Of course, these milestones are a bit biased to my own research, distributed computing, but I will describe that there are other areas interacting. And I organize these milestones into these categories. First, this is what is very nice, what I was saying. Some technology appears, and this suddenly motivates people building systems on those technologies. And the two milestones on technology were supercomputers, concurrency, shared memory supercomputers, the possibility of concurrent programming, and then network, the appearance of packet switched networks on the technology side. Then it's a very nice interactions of different areas. That one is cryptography, of course, the other is databases, and the other is distributed computing. And once these areas interact, then you need conceptual new ideas to move forward the science. And this are a few examples of the conceptual ideas that appear slowly over time. Some notions like transactions, notions like consensus, notions like digital signatures, notions like to understand the execution of a distributed system, that there's a whole spectrum of systems between very synchronous systems where processes run in rounds to completely asynchronous systems. But these are conceptual ideas. Once you have these conceptual ideas, then you need to implement them. And then you have algorithms that actually implement fault-tolerant consensus, that implement leader election, and so on. Efficient. One thing is to have the idea of a digital signature, and another is how do you implement it through an algorithm. And finally, you want to obtain a scientific theory that explains everything, that explains the limitations, like how many failures can be tolerated, impossibility results that say what are the limits of what can be done and what can be done, and some mathematical tools that allow you to analyze things in a uniform way. Like, so I will explain, topology plays an important role. Okay, so what are these few milestones? I mean, in fact, you can go back in time to what I call kind of prehistory, really. These are some milestones that are not really the modern milestones that I discovered, but actually they are really important. I mean, back to ancient Egypt, the notion of notaries was very important. The notion of ledgers. This is really the conceptual idea behind blockchain, that you want to implement a book, a ledger book, that is append only. You cannot cross any line. Each time something new happens, you append to the end of the ledger the new action that happened. So if you want to, this is kind of what happens in blockchains. If you want to know how money I have, it's not never written how money I have. It's just written the sequence of deposits and transfers of money, and you have to add them up to see actually how much money I have. So I mean, I don't discuss much of this because I mean, they really don't, are just early history ideas. But another set of very interesting early history ideas more recently is fault tolerance. That is also prehistory because it's still not influencing directly what we are doing today in distributed computing. But it's very interesting that actually in the 40s, 50s, and 60s, there was a huge amount of work on fault tolerance, because the first computers were made either of mechanical parts, relays, or electronic vacuum tubes that were extremely unreliable. So there was really a lot of so much effort, so many papers that already, I found a paper of 1971 that was already a survey of the many papers that were written about fault tolerance, even in those days. But the techniques, again, did not really influence much what we do today. They were kind of straightforward techniques of having a backup computer whenever, in case of the main one would fail, then the backup would enter and things like that. So this brings us really to the milestones that I want to discuss, which are more or less organized here, just to show you that these milestones, I think we can identify a group of very important milestones in a period of more or less 15 years, which is the green thing part that starts more or less in the mid-60s and ends in the early 80s. And in these 15 years, I think all of the main ideas were, or not all of them, but many of the main ideas really appeared, which are grouped by topic: databases, crypto, distributed computing, and below there are the systems that created this huge amount of work that I will mention: the Atlas supercomputer and the appearance of ARPANET in the early 70s. And then a few systems that were built still before understanding really what was going on, still without really a scientific computer science theory behind them. And so I will discuss a little bit of these milestones, and also if you would like to look at them in more detail after the talk. I included a list of them with the exact years and the authors of some of the papers that you can see after the talk. So what is in this? So what is the first? What the technology that really began to give the development is this first milestone of the Atlas supercomputer. In 1961, appears the most powerful computer in the world, even through the 60s and early 70s, and people began crazily and widely to write concurrent programs once this technology appeared. So again, this theme that first the technology appeared and people are excited, start writing programs on that, systems on that, but there was a total crisis. By the end of the 60s, a crisis was emerging. Programs were riddled with errors. People did not understand what was going on. It was many subtle errors, which was very difficult to catch, until the first milestone of conceptual inventions comes, that is Dijkstra notion of mutual exclusion, the idea that you have this abstraction, the mutual exclusion abstraction, and then of course implementations and theory opened the way for the first books of principles of concurrent programming and to fixing all these systems that were riddled with so many problems. And also it gave birth kind of to a sequence of the initial milestones about databases. The origins of distributed databases were exactly right after that in the early 70s. With these are three very seminal papers. The 74 paper of Johnson and Biller, which were actually kind of concerned with what we are considering in blockchains. How do you order this sequence of commands that appear concurrently everywhere? So they had the same problem, and they started to inventing the main notions that we use in several places, like timestamping. And how do you do this timestamping in a distributed way? The 75 paper of Steve Bunch said, well, let's have kind of a central sequence generator, which is a bit what we do in blockchain through some form of consensus. And then after those initial papers, then finally to do those in a resilient way, in a fault-tolerant way, the very important paper, a seminar paper of Alsberg and Day, that came up with the notion of primary backup approach, which is somehow apparently still the most widely used fault tolerance technique in database theory. In databases, I mean. And then the second technological big impact was the appearance of the ARPANET in 1971. Created a lot of excitement. Suddenly computers could talk with each other, and people, and also provided already the basic primitives that we all know, FTP, email, rlogin, and the first one to implement TCP/IP. Tremendous excitement. People started to realize we can do many things, build systems now on top of computers that communicate with each other. And this is and distributed resource sharing and so on. So these are two examples, a couple of examples of systems that were built, early systems that were built once the internet appeared, which were still without understanding really what was happening. In 1975, the Stony Brook system, which was aimed at building a flexible communication facility between processes. So in distributed computing, really a lot of the emphasis was in fault tolerance, while from databases was a lot correctness and transactions and so on. And this I will cite directly from that paper of 75, the Stony Brook paper. Suddenly, quite towards the end of the paper, you encounter a story and they say, I mean, we don't understand really what's going on with our system. We are struggling to design it so that it tolerates failures, but we somehow have the intuition that this cannot be done, actually, that it's impossible to do what we are trying to do with our system. And they describe this story. Okay, so I'm quoting from the paper they describe. We have they try to have an abstraction. People were building systems, and this is an early example of how you try to have an example of what we are actually trying to do in a more abstract way. And they describe a story. Gangsters divided into groups are about to pull off a big job. Some of the men are holed up in a warehouse across town, awaiting for precise instructions from another group. And the goal is that it's absolutely essential that the two groups act with complete reliance on each other in executing the plan at the same time. Either both attack the bank or neither of them attacks the bank. And the problem is that they can communicate only by unreliable messages. This is what they say in the paper, just like that. And then they continue saying, of course, they will never get around to putting the plan in actions because simultaneity cannot be achieved by this means, without any formal proof, no formal model even. And so this is a nice example that really motivated people to see, well, what is exactly we can do and we cannot do in a fault-tolerant way. And of course, a sequence of papers by Lamport and others were motivated because exactly this situation, that there was no clear understanding of the systems that were being built, how many failures could be tolerated, and so on. And Lamport himself was working on one other system that was very influential, the SIFT software implemented by fault tolerance. And here also Lamport tells us it was generally assumed that tasks are redundantly executed by three computers, and thus a single failure can be tolerated using voting. I took this quote from one of these early papers. So of course, when we have the first milestone of really a theoretical scientific paper on principles of distributed computing in 1978, the reaching agreement in the presence of faults is what really we call today the Byzantine general problems, which was this informally described problem in the SIFT project with the gangsters. And then they formally showed that actually what people believed that could be done, actually it could not be done, with really a formal proof of proving that if you want to have an agreement between n processes, you need 3 n+1 processes to tolerate n faults. And people before would think, well, if you have 3n replications should be enough because of voting arguments, but actually no, you cannot. And also the first maybe introduction of the interaction of cryptography with distributed computing, where it was observed that if you can use digital signatures, actually you need only 2 n+1 processes to tolerate n failures. Okay, so these are the first abstractions, the really advances of foundations, consensus, coordination, Byzantine agreement, the first impossibility results. And I would like to just to describe a little bit how already in these initial ideas another interesting thing was discovered, that actually the impossibility is actually of a topological nature, which also played an important role over the next developments. Because and also because people notice that coordination is needed all over. Actually, if you have taken any course on internet and TCP, you know that simply what TCP is trying to do is simply impossible, because it's again trying to coordinate, can't guarantee state consistency between endpoints. Transactions in databases, of course, is a form of coordination, which theoretically it's impossible. And it's a key concept in other areas, common knowledge and other areas, and other generalizations that provide a basis for what are the realistic expectations of that we can achieve with our distributed system. So how do you prove this impossibility that was informally stated in the initial paper of Akiyu and Huber? I will describe it just as two insecure lovers, which is essentially, instead of gangsters, but trying to be a bit more positive and more precise. Alice and Bob want to schedule a meeting. If both attend, it's good. If only one attends, it's bad. Then communication is only by SMS messages. You know that usually they arrive, the SMS messages, fast and on time, but also you know that sometimes they may be lost or may be delayed. And still Alice and Bob want to schedule a meeting in a way that either both attend or neither of them attends. So how do you prove this impossibility? I will just show it in a few slides, and you can understand already what is an essential part behind many of the impossibilities that we have in distributed computing is this topological continuity. So let me consider even the simplest situation where Alice has two possible preferences. Alice wants to either meet at dawn or meet at noon. And these two initial situations, local states of Alice, because it's what is in her mind. Bob doesn't know at what time she wants to meet. So are represented by two black vertices. And in the middle, these two black vertices are connected to a single vertex, which is this local state of Bob, which simply has nothing in his mind. He says, I'm just waiting for my dear lover to see at what time she wants to go to the movies. And then, so there are two global states of this system, two possibilities. One is the edge on the left, which is Alice wants to meet at one time, and the other is the edge of where Alice wants to meet at another time. And these edges represent global states of the system, but at the same time, each edge has endpoints, which are the local vertices, which are the local perspectives about the global state. So you can see that Bob belongs, the local state of Bob belongs to two possible worlds because he doesn't know in which one we are living. And Alice really knows which of the two globes. And now Alice has to send an SMS to Bob to say, let's meet at this time, as we do in real life. So Alice sends a message. And now we have to analyze what is the evolution of a possible protocol to solve this problem of coordinating that we know it's impossible. So we assume for contradiction that there is some protocol by which Alice decides to send an SMS message, and we analyze what happened 1 unit of time after that, and we say, well, there are two possibilities. Either the message arrived, usually it arrives, but we are not sure. Usually the SMS message arrived, but it might not have arrived. So what happens here, you can see that if the message doesn't arrive, then still the local state of Bob still is shared by the two sides of the line, where still Bob doesn't know at what time Alice wants to arrive. And if the message is delivered, then now Bob knows at what time. So now you have four possible, we started with two possible global states of what could be of the system. And now you, after one unit of time, you have now four possible global states, the four edges. And in each edge, you have the perspective of what each one saw. The message delivered or not delivered. But of course, Alice now you can see that Alice is the one that doesn't know if her message arrived or not. So you say, okay, I don't know which is their protocol. They will send back and forth messages. Alice sends the first message saying, my love, I want to meet at that time. And Bob answers, yes, my love. Bob has to send an acknowledgement because Bob knows that Alice doesn't know if her acknowledgement arrived and so. And you can see that a simple inductive argument says that each new phase of acknowledging the acknowledging, yes, my love, I really love you. I will really go to that time at school. Each one of the last acknowledgement also can either arrive or not arrive, and this makes the line longer and longer because in the extremes there are still the two possibilities that the last message might have arrived or might not have arrived, and this hypothetical protocol at some point has to terminate. And the impossibility says that no number of even successfully delivered acknowledge will be enough because the graph of possible states gets longer and longer but remains connected. And you can see in the picture, we start with a connected input graph. Then you assume some sequence of back and forth messages by Alice and Bob until they terminate, and you have some long sequence of possible states after termination, and those local states have to be mapped into decisions. Well, at what time do we go to the movies? Either we meet at dawn or we meet at noon, and these are two disconnected edges, where in each edge, each of them knows at what time they are going to meet, and you can intuitively see that it's very clear that you cannot map a connected long path into two disconnected components. So this is the whole idea between the original problem that was studied in those years and a proof on how the issue is of a topological nature. You start with a shape and you subdivide, you modify the shape by stretching it, making it longer, but you need to break it in order to make a consensus decision, and you can never break it in this model where the messages may or may not arrive. And this is, in some generality, what has been explored since the famous Herlihy and Shavit theorem of 1993, and that we overview in the book with Maurice, which I will not get into it, but just I would like to mention that this really opened the way to have a scientific unifications of the many models, shared memory. We had supercomputers with concurrency and shared memory, and others with message passing. We studied many different types of failures independently, like crash failures and Byzantine failures, or even dependent failures. You have message passing with even different communication objects, test and set, in addition, compare and swap, and so on. Synchronous, this gamma of synchronous to partially synchronous systems that are so important for blockchains and other applications. And we can have a kind of a unified understanding instead of writing each time another paper for each one of the combination of these things. And just to give you a flavor of what happens when you go from 2 processes, Alice and Bob, you go to 3. The only thing that changes really is instead of edges, we had edges because each world has 2 perspectives, the perspective of Alice and the perspective of Bob. Now if you have 3 agents, you have for each world, which is a triangle, you have what is the local state of each one of the 3 participants. If these are binary inputs, say for consensus, you have a triangle where the 3 processors have input 0, another triangle where the 3 have input 1, and all the combinations. And now you run a system in some model, maybe SMS messages like Alice and Bob, or maybe another. But you see that when you consider this perspective, you immediately see that there is some shape, some geometric shape emerges in this kind of a triangulated sphere, yeah, which is what we call the input complex. And then you run it on some system, like in case of the Alice and Bob, some kind of asynchronous system. And what the main result of Herlihy and Shavit said that always the shape of the initial input complex will be completely preserved. The only thing that will happen is that it gets subdivided into finer and finer triangles. And this implies the impossibility of several problems in asynchronous computation, but also in synchronous models, like we try to analyze blockchains in kind of a partially synchronous model, so you can do the same. But now you see that when your system is more and more synchronous, you can solve more and more problems. Why? Because now the topology is not completely preserved. Eventually you succeed into breaking the initial shape into something disconnected, and once you succeed, then you can solve consensus and other problems that require a disconnected shape. And you can see that you can prove lower bounds of how long, how many rounds of communication you need in order to finally break the shape and succeed into solving a problem. Okay, so let me discuss some conclusions about the milestones and so on. It all started in the 70s when it became clear that computers were going to fly commercial aircraft. This is a story that Lamport tells us. It all started in the 70s when it became that computers were going to fly commercial aircraft. And then you needed replication because you wanted to have replicated sensors, replicated computers on board in case one would fail, and so on. So NASA began funding research to figure out how to make them reliable enough for the task. And this was actually part of the initial systems that were being built, still without a clear theoretical understanding of what happened. And Lamport tells us, over the years, I often wondered whether the people who actually build airplanes know about the problem of Byzantine failures. In the late 80s and early 90s, the people at Boeing working on military aircraft and on the space station, and the people at McDonnell Douglas did not understand still Byzantine fault tolerance. So now, I mean, with our creature, we have come a long way since the time distributed systems were being built without understanding what exactly the problem being solved was and which failures were tolerated. And also we finally understood why distributed computing is so different from sequential computing. Even initially in theoretical computer science, we thought, oh, kind is one Turing machine or a multi-tape Turing machine is kind of the same thing. But now we understand that no, it's really different, completely different things, distributed computing and sequential computing, because distributed computing is really a matter of, in some sense, the science of perspectives. And what is interesting is that these perspectives evolve with time. This is what happens when we communicate with each other. We change our perspective of what other people think and what could be nobody can observe the global state of the system, but we all have different perspectives that are evolving as we evolve. The way they evolve depend on the environment, whether it's a completely synchronous or completely asynchronous, partially synchronous, and what type of failures, and so on. So this is my overview.
Thank you.